The goal for the next few lectures is to prove Freiman's theorem, which we discussed last time. Right, so we started with this tool that we proved called the Ruzsa inequality, which tells us that if you have a set A now in an arbitrary abelian group, and if A has controlled doubling, if it has bounded doubling, then all the further iterated subsets have bounded growth as well. Okay, so this is what we proved last time. And okay, so we're going to be using the Ruzsa inequality many times. But there are some other tools I need to tell you about. Okay? So the next tool is known as Ruzsa covering lemma. All right. So let me first give you the statement, and then I'll explain some intuition. I think the technique is more important than the statement, but in any case, here's what it says. If you have x and b, they are subsets of some arbitrary abelian group. If you have the inequality that x plus b is at most k times the size of b, so the size of x plus b is at most k times the size of b, then there exists some subset t of x with the size of t being at most k, such that x is contained in t plus b minus b. Okay, so that's the statement of Ruzsa covering lemma. So let me try to explain what it is about. Okay. So the idea here is that if you're in a situation where if it looks like, so you should think of B as a ball. Right? So if it looks like x plus b might be coverable by k translates of b. So here, you're supposed to think of b like a ball in a metric space. Then x is actually coverable. So if it looks like, meaning just by size alone, by size info alone, so just based on the size, if it looks like x plus b might be coverable by k different translates of b, then actually x is coverable, but you have to use slightly larger balls by k copies of b minus b. So you should think of b minus b as slightly larger balls than b itself. Right? So if b were an actual ball in Euclidean space, then b minus b is the same ball with twice the radius. So Ruzsa covering lemma is a really important tool. The proof is not very long, and it's important to understand the idea of this proof. Right? So this is a proof not just in additive combinatorics, but something that happens, it's a standard idea in analysis. Right? So it's very important to understand this idea. And the key idea here, I think the proof is more important than the statement up there. The key idea here is that if you want to produce a covering, one way to produce a covering is to take a maximal packing. A maximal packing using with balls, for instance, implies a covering with balls twice as large. Okay, so let me illustrate that with a picture. Suppose you have some space that I want to cover. But you get to use, let's say, unit balls. So how can I make sure I can cover the space using unit balls, and I don't want to use too many unit balls? So what you can do is, let me start by a maximal set of unit balls, so with centers, so it's now half unit balls, so the radius is 1/2. Okay, so I put in as many as I can so that I cannot put in any more. So that's what maximal means. Mole here doesn't mean the maximum number, although if you put in the maximum number, that's also okay. But maximal means that I just cannot put in any more balls that are non-overlapping. Then if I have this configuration, now what I do is I double the radii of all the balls. Okay, so whoever takes today's notes will have a fun time drawing this picture. So this has to be a covering of the original space. Right? Because if you had missed some point, I could have put a blue ball in. Yes?
What if the space has some narrow portion?
Question, what if the space has some narrow portion? It doesn't matter. Right? So if you formulate this correctly, so if you miss some point. So here, so it depends on how you formulate this, this covering. So the point is that if you take a maximal set of points, when you expand, you have to cover the whole space. Because if you missed some point, right? So imagine if you had, for example, if suppose you missed, well, okay, I mean, it's okay. Suppose you had missed some point over here, then I could have put an extra ball in. Right? So if you had missed some point over here, then it means that I should have been able to put in that ball there initially. Okay, so it's a very simple idea, but a very powerful idea. And it comes up all the time in analysis and geometry, and it also comes up here. Okay, so let's do the actual proof. So now let me let T be a subset of X, be a maximal subset of X such that the sets little t plus b are disjoint for all elements little t of the set big T. Okay, so it's like this picture. I pick a subset of X so that if I center balls around these T's, then these translates of B's are disjoint. Then you put in a maximal such set. Okay, so due to the disjointness, we find that the product of the sizes of T and B equals to the size of the sum, because there's no overlaps. But T plus B has size at most X plus B, because T is a subset of X. But I also, from the assumption, we knew that X is size of X plus B is upper bounded by the size of B times K. So in particular, we get that the size of T is at most K. Okay, so in other words, over here, the number of blue balls you can control by simply the volume. Now, since T is maximal, we have that for every little x, there exists some little t such that the translate of B given by X intersects one of my children translates. Because if this were not true, then I could have put in an extra translate of B. So in other words, there exist two elements B and B prime such that T plus B equals to X plus B prime, and hence X lies in little t plus B minus plus B minus B, which implies that the set X lies in T plus B minus B. Okay, so that's the Ruzsa covering lemma. So it's an execution of this idea I mentioned earlier that a maximal packing implies a good covering. Any questions? All right, so now we have this tool. We can prove an easier version of Freiman's theorem, where instead of working in the integers, we're going to work in the finite field model. Okay, so usually it's good to start with finite field models. Things are a bit cleaner, and in this case, it actually only requires a subset of the tools that we'll need for the full theorem. So instead of working in finite field model, we're going to work in something just slightly more general, but it's the same proof. So we're going to be working in a group of bounded exponent. Freiman's theorem in groups of bounded exponent, and the word exponent in group theory means the following. So the exponent of an abelian group is the smallest positive integer if it exists. Okay, so the smallest positive integer r, so that Rx equals to 0 for all x in the group. So for example, if you are working in fp to the n, then the exponent is p. So every element has, if you add it to itself r times, then it destroys vanishes the element. The name of the word exponent comes from, you can define the same thing for non-abelian groups, in which case you should write this expression using the exponent, right, instead of addition. You have multiplication. So that's why it's called exponent, so the name is stuck even though we're still working in the additive setting. We're going to write this, so the angle brackets to mean the subgroup generated by the subset A. So A is a subset of the group elements. And so the exponent of a group then is equal to the maximum number of, so if you pick a group element, look at how many group elements does it generate. Okay, so it's equal to the max. All right, so the example you can have in mind is f2 to the n, which has exponent 2. So in general, we're going to be looking at a special case in a group with bounded exponent. Right? And Freiman's theorem in this case is due to Ruzsa, who showed that if you have a finite subset in an abelian group, with exponent r, so finite exponent, if A has doubling constant at most k, then, okay, so what do we want to say? We want to say, just like in Freiman's theorem, that if A has bounded doubling, then it is a large portion of some structured set, and here structured set means subgroup. Well, if you're going to be looking at subgroups that contain A, you might as well look at the subgroup generated by A. So the claim then is that the subgroup generated by A is only a constant factor bigger than A itself. Okay, so let me say it again. If you have a set A in a group of bounded exponent and A has bounded doubling, then conclusion is that A is a large proportion of some subgroup. Conversely, we saw last time, if you take a subgroup, it has doubling constant 1. So if you take a positive proportion, a constant proportion of the subgroup, it also has bounded doubling. And this statement is in some sense a converse of that observation. This bound here is not optimal. I'll make some comments about what we know about these bounds. But for now, just view this number as a constant. Okay. Any questions about the statement? All right. Okay, so let's prove this Ruzsa's theorem, giving you Freiman's theorem in groups with bounded exponent. So we're going to be applying the tools we've seen so far, starting with Ruzsa. Okay, so by Ruzsa inequality, we find that, okay, so I'm going to write down some expression. You might wonder why this expression, because we're going to apply covering lemma in a second. Right? So this set by Ruzsa, its size is bounded because the set can also be written as 3a minus a, so its size is bounded by k to the 4th times size of a. So Ruzsa is a very nice tool to have. It basically tells you if you have bounded doubling, then all the other iterated sums are essentially controlled in size. And then we're using that here. Okay, so now we're in the setting where we can apply the Ruzsa covering lemma. Okay, so by covering lemma, we're going to apply the covering lemma, so using the notation earlier, with x equal to 2a minus a and b equal to a. By covering lemma, there exists some t being a subset of 2a minus a, with t not too large because of our earlier estimate, and such that 2a minus a is contained in t plus a minus a. All right, so it's easy to get lost in the details. But what's happening here is that I start with A, and I'm looking at how big these iterated growing sum sets can be. Right? And if I keep on doing this operation, like if I just apply Ruzsa, I can't really control the iterated sums by an absolute bound. This bound will keep growing if I take bigger iterations. But Ruzsa covering lemma gives me another way to control the bounded iterations. It says there's some bounded set T such that this iterated sum is nicely controlled. So let me iterate this bound even further. We're going to iterate the containment by adding a to both sides. So a to both sides, and we obtain that 3a minus a is contained in t plus 2a minus a. But now 2a minus a was contained in t plus a minus a, so you get 2t plus A minus A. Okay, so now we've gained quite a bit because we can make this iteration go up, but not at the cost of iterating A, but at the cost of iterating T. But T is a bounded size. Right? T is bounded size, so T will have very nice control. We'll be able to very nicely control the iterations of T. So if we keep going, so we find that for all integer n, positive integer n, n plus 1 A minus A is contained in nt plus A minus A. But for every integer n, the iterated sums of T are contained in the subgroup generated by T. So therefore, if we take n to be as large as you want, see that the left-hand side eventually becomes the subgroup generated by A, and the right-hand side does not depend on n. So you have this containment over here. We would like to estimate how large the subgroup generated by A is. So we look at that formula, and we see that the size of the subgroup generated by T, and here is where we're going to use the fact that the assumption that the group has bounded exponent. So think F2 to the n, if you will. In F2 to the n, if I give you a set T, what's the space, subspace spanned by T? What's the maximum possible size? Right, so most 2 raised to the number. Right, so in general, you also have that the subgroup generated by T has size at most R raised to the size of T in a group of exponent R, which we can control because T has bounded size. And the second term, A minus A, so we also know how to control that by Ruzsa. Therefore, okay, so putting these two together, we see that the size up here is at most r to the k to the 4 times k squared size of A, which is the bound that we claimed. Okay. Any questions? Right, so the trick here is to only use Ruzsa somehow a bounded number of times. If you use it too many times, you can't, this bound blows up. But you use it only a small number of times, and then you use the Ruzsa covering lemma so that you get this bounded set T that I can iterate. Let me make some comments about the bounds that come out of this proof. Right? So you get this very clean bound just following this proof. But what about examples? Right? So what kinds of examples can you think of where you have a set of bounded doubling, but the set generated, the group generated by that set is potentially large? Right? So even in F2, in F2 to the m, right? So if A is an independent set, so a basis or subset of a basis, for instance, then K, so A is independent set, so all the pairwise sums are distinct. So K is about the size of A over 2. That's the doubling constant. Whereas the group generated by A has size 2 to the size of A, which is around 2 to the 2k times the size of A. Okay, so you see that you do need some exponential blow up from k to this constant over here. And it turns out that's more or less correct. So, the optimal constant for f2 to the n is now known very precisely. As in, if you give me a real value of k, then I can tell you, there are some recent results that tells you exactly what is the optimal constant you can put in front of the a. So very precisely. But asymptotically, it looks like 2 to the 2k divided by k. So that's what it looks like. So this example is basically correct. For general R, we expect a similar phenomenon. So Ruzsa conjectured that in the hypothesis of the theorem, the constant you can take is only exponential in k. So R to the some constant, c times k. And it has been verified for some values of R, but not in general. So known for some R, for example, primes. Okay, any questions? All right, so this is a good milestone. So we've developed some tools, and we're able to prove an easier version of Freiman's theorem in a group of bounded exponent. And you can ask yourself, does this proof work in the integers? And well, literally no, right? Because if you look at this proof, this set here is infinite. Unlike in a finite field setting, in the integers, well, that's not very good. So the strategy of Freiman's theorem, the proof of Freiman's theorem, is to start with the integers and then try to not work in the integers, but try to work in a smaller group. Even though you start in a maybe very spread out set of integers, I want to work in a much smaller group so that I can control things within that group. And this is an idea called modeling. So I have a big set and I want to model it by something in a small group. So okay, we're going to see this idea. But to understand what does it mean to have a good model for a set in the sense of additive combinatorics, I need to introduce the notion of Freiman homomorphisms. So one of the central philosophies across mathematics is that if you want to study objects, you should try to understand maps between objects and understand properties that are preserved under those maps. Right? So if you want to study groups, I don't really care how you label your group elements by 1, 2, 3 or ABC. What I care about is the relationships, and those are the data that I care about. And then, of course, then you have concepts like group homomorphisms, group isomorphisms that preserve all the relevant data. Right? Similarly, in any other area, in geometry, you have manifolds. You understand not specifically how they embed into space, but what are the intrinsic properties. Right? So we would like to understand what are the intrinsic properties of a subset of an abelian group that we care about for the purpose of additive combinatorics and specifically for Freiman's theorem. And what we care about is what kinds of additive relationships are preserved. And Freiman's homomorphisms capture that notion. So roughly speaking, we would like to understand maps between sets in possibly different groups. In possibly different abelian groups that preserve, but only partially preserve, additive structure. Okay, so here's a definition. Suppose we have A and B, and they're subsets between subsets in possibly different abelian groups. Could be the same, but possibly different. And everything's written under addition as usual. So we say that a map phi from A to B is a Freiman S homomorphism. So that's the term, Freiman S homomorphism. Sometimes also the Freiman homomorphism of order S. Okay, so that's equivalently, I can call it that as well. If the following holds. If we have the equation phi of A plus plus phi of A sub S equal to phi of A prime 1 plus plus phi of A prime S. Whenever A through AS, A prime through AS prime, so A1 prime through AS prime, satisfy the equation A1 plus plus AS equal to A1 prime plus plus AS prime. Okay, so that's the definition of a Freiman S homomorphism. It should remind you of the definition of a group homomorphism, right, which completely preserves additive structure, let's say between abelian groups. And for Freiman homomorphisms, I'm only asking it to partially preserve additive structure. So the point here is that if I only care about, let's say, pairwise sums, if that's the only data I care about, then Freiman S homomorphisms preserve that data. Okay. To give you some, okay, so one more thing. If phi from A to B is furthermore a bijection, okay, and both phi and phi inverse are Freiman S homomorphisms, then we say that phi is a Freiman S isomorphism. Okay, so it's not enough just to be a bijection, but it's a bijection, and both the forward and the inverse maps are Freiman Freiman homomorphisms. Okay, so these are the definitions we're going to use. Let me give you some examples. Okay. So every group homomorphism is a Freiman homomorphism of every order. So group homomorphisms preserve all additive structure, and Freiman homomorphisms only partially preserve additive structure. A composition, so if phi1 and phi2 are Freiman S homomorphisms, then phi1 composed with phi2 is a Freiman S homomorphism. Okay, so compositions preserve this property, and likewise, if you have, instead of homomorphisms, if you have isomorphisms, then that's also true as well. Okay, so these are straightforward things to check. So a concrete example that shows you a difference between group homomorphisms and Freiman homomorphisms is, suppose you take an arbitrary map phi from a set that has no additive structure. Okay, so it's a 4-element set, has no additive structure, and I map it to the integers, claim that this is a Freiman 2 homomorphism. Okay, so you can check, right? So you can, whenever this is satisfied, but that's never non-trivially satisfied. So an arbitrary map here is a Freiman 2 homomorphism. And if, furthermore, so if you have, let's say, a bijection between two sets both having no additive structure, if it's a bijection, then it's a Freiman isomorphism of here order 2. Okay. Let me give you a few more examples. So in when you look at homomorphisms between finite groups, so you know that if you have a homomorphism and it's also a bijection, then it's an isomorphism. But that's not true for this notion of homomorphisms. Right? So the natural embedding so the natural embedding that sends the Boolean cube to the Boolean cube, but viewed as z mod 2 to the n. Okay, so so what's happening here? This is a part of a group homomorphism. Right? So if you look at z to the n, and I do mod 2, and I restrict to this Boolean cube, that's the group homomorphism. If I view this as a subset of a bigger group. So it is a Freiman homomorphism of every order. And it's bijective, but it is not a Freiman 2 isomorphism. Because you have additive relations here that are not present over here. Right? So if you read the definition, the inverse map, there are some additive relations here that are not preserved if you pull back. Okay. So here's another example that will be more relevant to our subsequent discussion. The mod n map. So the mod n map, which sends z to z mod n. So this is a group homomorphism. So hence it's a Freiman homomorphism of every order. But it's not, okay, so if you look at this map, and even if I restrict to here, okay, so it's not an Freiman isomorphism, just like earlier. However, okay, so so let me go back to z again. So if A is a subset of integers with diameter less than n over s, then this map, mod n, maps a Freiman S isomorphically onto its image. So even though mod n restricted to 1 through n is not a Freiman isomorphism of order 2, if I restrict to a subset that's, let's say, contained in some small interval, then all the additive structures are preserved. Okay, so let me show you why. So this is not too hard once you get your head around the definition. Right. So indeed, if you have group elements A1 through AS, A prime 1 through A prime S, and if they satisfy the equation so if they satisfy this equation, so we're trying to verify that it is a Freiman S isomorphism, namely the inverse of this map is a Freiman S homomorphism. So if they satisfy this equation, so this is them satisfying this additive relation in the image in Z mod n, then note that the left-hand side, so all of these A's are contained in a small interval because the diameter of the set is less than n over s. So if you look at how big A1 minus A1 prime can be, it's at most what's less than n over s in size. So the left-hand side in absolute value, viewed as an integer. Right, so the left-hand side is less than n in absolute value, since the diameter of A is less than n over s. So you have some number here which is strictly less than n in absolute value and is 0 mod n. So it must be actually equal to 0 as a number, as an integer. Okay? So this verifies that the additive relations up to sy sums are preserved under the mod n map if you restrict to a small interval. All right. Any questions so far? All right, so in additive combinatorics, we are trying to understand, properties, specific additive properties, and the notion of Freiman homomorphisms and Freiman isomorphism capture, what specific properties we need to study and what are the maps that preserve those properties. And the next thing we will do is to understand this model lemma, the modeling lemma, that tells us that if you start with the set A with small doubling, initially A may be very much spread out in the integers. Right? It may have very large elements, very small elements, very spread out. But if A has small doubling properties, then I can model A by a small, inside a small group, such that all the relevant data, namely relative to these Freiman homomorphisms, are preserved under this model. Okay, so let's move on to the modeling lemma. The main message of the modeling lemma is that if A has small doubling, then A can be modeled. And here, that means being Freiman isomorphic to a subset of a small group. Okay, so first as a warm-up, let's work in the finite field model just to see what such a result looks like. And it contains most of the ideas, but it's much more clean. It's much cleaner than in the integers. So in the finite field model, specifically f2 to the n. Okay, so what do we want to say? suppose you have A, a subset of f2 to the m, and suppose that m is some number such that 2 to the m is at least as large as SA minus SA. Okay, so remember from Plüniker Ruzsa, you know that if A plus A is small, then this iterated sum is small. So suppose we have these parameters and sets. The conclusion is that A is Freiman S isomorphic to some subset of f2 raised to m. All right, so initially, A is in a potentially very large vector space, or it could be all over the place. And what we're trying to say here is that if A has small doubling, so if A has small doubling, then by Plüniker Ruzsa, SA minus SA has size not too much bigger than A itself, only a bounded times the size of A itself. So I can take an M so that the size of this group is only a constant factor larger than the size of A itself. So we're in a pretty small group, right? So we are able to model A, even though initially it sits inside a pretty large ambient group, by some subset in a pretty small group. All right, so let's see how to prove this modeling lemma. So the finite field setting is much easier it's not too hard to deal with, because we can look at linear maps. Okay? So the following are equivalent for linear maps phi, okay, so for group homomorphisms. So phi is a Freiman S isomorphism when restricted to A. So here phi, I'm going to let it be a linear map from f2 to the n to f2 to the m. The following are equivalent. Okay. So we would like phi to be a Freiman S isomorphism when restricted to A. So this means that I restrict to A and I restrict to its image. So it's Freiman isomorphically maps onto the image. Okay, so what does that mean? So, well, if phi is already a homomorphism, so it's automatically a Freiman S homomorphism. For it to be an S isomorphism, it just means that there are no additional linear relations in the image that were not present earlier, which means that phi is injective on SA. Okay, so just think about the definition. And in the definition, if you know additionally that phi is a homomorphism, everything is much cleaner. It is also equivalent to that phi of x is non-zero for every non-zero element x of SA minus SA. Okay, so this is a very clean characterization of what it means to be in Freiman S isomorphism when you are in a abelian group and you have linear maps. You have homomorphisms. So if we start by taking phi to be a uniformly random linear map. Okay, so in particular, for example, you pick a basis and you send each basis element to a uniformly random element. Then we find that if 2m is at least SA at minus SA, then, okay, so let me call these properties 1, 2, 3. So then the probability that 3 is satisfied is positive. Because each element of SA minus SA, well, I can also ignore 0. So each non-zero element of SA minus SA is, violates this property with probability exactly 2 to the minus m. Everything's uniform. Okay? So if there are very few elements and the space is large enough, then the third bullet is satisfied with positive probability. So you get a Freiman S isomorphism. Okay. Any questions? So to get this model, in this case, in the finite field setting, it's not so hard. So you kind of project the whole set, even though initially it might have be very spread out into a lot of dimensions. You project it down to a small dimensional subspace randomly. And that works. So that with high probability preserves all the additive structure that you want, provided that you have small doubling. Now let's look at what happens in Z. So in Z, things are a bit more involved, but the ideas, actually a lot of the ideas come from this proof as well. So Ruzsa's modeling lemma tells us that if you have a set of integers, always a finite set, and integers s and n are such that n is at least SA minus SA, then, okay, so it turns out you might not be able to model the whole set A, but it will be good enough for us to model a large fraction. So then there exists an A prime subset of A with A prime being at least an S fraction of the original set. And A prime is Freiman S isomorphic to a subset of Z mod n. Okay, so same message as before with extra, so with an extra ingredient that we did not see before. But the point is that if you have a set A with controlled doubling, then, well, now you can take a large fraction of A that is Freiman isomorphic to a subset of a small group. This is small because we only need n to exceed SA minus SA, which only constant factor more than the size of A. Yeah?
Is s greater than 2 comma n? Or
Sure. X greater than 2 separately, and some integer. Yeah. Thank you. Okay, so in our application, s will be a constant. S will be 8. Right? So think of s as some specific constant. Okay, any questions? Okay, so let's prove this, this modeling lemma. We want to try to do some kind of random map. But it's not clear how to start doing a random map if you just start in the integers. So what we want to do is first place ourselves in some group where we can consider random automorphisms. Right. So we start by perhaps very wastefully choosing a prime Q bigger than the maximum possible SA minus SA. Okay, so just choose a large enough prime. I don't care how large you pick. Just Q can be very, very large. Okay. So pick a prime. And now I work inside Z mod Q. I notice that if make Q large enough, then A sits inside Z mod Q Freiman isomorphically, or S isomorphically. So just pick Q large enough so that you don't have to worry about any issues. So yeah, so the mod Q map from A to Z mod Q, right? So it's Freiman isomorphic, Freiman S isomorphic onto its image. So let's now consider a sequence of maps. And we're going to denote the sequence like this. So we start with Z. So that's where A originally sits. And maps to Z mod Q. So that was the first map that we saw. And now we want to do a random automorphism, kind of like the random map earlier. But in Z mod Q, there are lots of nice random automorphisms, namely multiplication by some non-zero element. And finally, we can consider the representative map, where every element of Z mod Q, I can associate to it a positive integer from 1 to Q, which agrees with it, Z mod Q. Right? So the final step is not a group homomorphism. So we need to be more careful. So let me denote by phi this entire map. Right? So from the beginning to the end, so this composition, I'll denote by phi. And lambda here is some element between 1 and Q minus 1. Now, remember what we said earlier, that this map, this final map here, might not be a Freiman homomorphism because there are some additive relations here that are not preserved over here. But if I restrict myself to a small interval, then it is a Freiman homomorphism if you restrict to that interval. Right? If you restrict yourself to an interval, you cannot have extra relations over here because they cannot, the interval is small enough, you can't wrap around. So let's consider restrictions to small intervals. But I start with A over here. So I want to restrict myself to some interval so that I still have lots of A in that restriction. And you can do this by pigeonhole. So by pigeonhole, for every lambda, there exists some interval. We'll denote by I sub lambda inside Q. Okay, so the length of this interval will be at most Q over S, such that if I look at the restriction of this interval, I pull it all the way back to the beginning, then I still get lots of elements of A. So A sub lambda, meaning the elements of A whose map gets sent to this interval, has at least A over S elements. Okay, so for instance, you can chop up Q into S different intervals. So one of them will have lots of elements that came from A. Okay. And this is why, in the end, we only get a large subset of the A. We're going to forget about everything else and focus our attention on this set here. Okay. So thus, by our earlier discussion having to do with the final map being the Freiman S homomorphism when you're working inside a short interval, we see that phi, if you restrict to this A sub lambda, is a Freiman S homomorphism. Okay. Each step is a Freiman homomorphism because it's a group homomorphism, and the final step in this restriction is also a Freiman homomorphism, Freiman S homomorphism, because what we said about working inside short intervals. Okay, so this part is very good. All right, so now let me consider one more composition. So at the end of the day, we would like to model this A lambda inside some small cyclic group. Okay, so far we don't have small cyclic groups yet. but I'm going to manufacture a small circular group. Okay, so we're going to consider the map where first you take that phi all the way until the end, and now you take a mod m map. Right, so if I don't write anything, if it goes to z mod m, it means the mod m map. Right, so let me consider phi, psi, let me consider psi, which is the composition of these two maps. All right, so we would like to say that you can choose this lambda so that this A sub lambda gets mapped Freiman S isomorphically until to the end. So far, everything looks pretty good, right? So you have Freiman S homomorphism, and you have a group homomorphism, so you have so the whole thing is a Freiman S homomorphism. So phi, the psi is restricted to A sub lambda is a Freiman S homomorphism. But now the thing that we really want to check is if there are some relationships that are present at the end in Z mod M that were not present earlier. And so we need to check that, and we claim that if psi does not map A sub lambda Freiman isomorphically, then something has to have gone wrong. Right? So if it does not map A sub lambda Freiman isomorphically onto its image, then so what could have gone wrong? Claim that there must be some d, which depends on lambda, in SA minus SA, okay, and d is not 0, such that phi of d is 0 mod m. Okay, so we'll prove this. But like before, it's a very similar idea to what's happening earlier. The idea is that if you have we want to show that there are no additional additive relations in the image. So we would like to, so if it's not a Freiman isomorphism, then there has to be some accidental collisions. And that accidental collision has to be witnessed by some d. Okay, so this requires some checking. So suppose, indeed, okay, so suppose the hypothesis, suppose that the psi does not map A sub lambda Freiman S isomorphically onto its image, then there exists A1 through AS and A1 prime through AS prime in A lambda, such that they do not have additive relation, but their images do have this additive relation. Now, their images, all the way until the end, having the additive relation means that phi has this additive relation mod m. Okay, so how can this be? Recall that since the image, so all of these elements lie inside some short interval. The interval has length less than q minus s. Okay, so we saw this argument, very similar argument earlier before the break. because everything lies in a short interval, you see that this difference between the left and the right-hand sides this difference is strictly less than q. Now, by switching the a's and a primes if necessary, we may assume that this difference is non-negative. Okay, so otherwise, it's just a labeling issue. Otherwise, I relabel them. So then this here, so what's inside this expression, okay, so let me call this expression inside the absolute value, call it star. So then, star is some number between 0 and strictly, so at least 0 and strictly less than q. Right. So if we set d to be okay, so d to be this expression, so sum up, so the difference between these two sums. On one hand, this d here, sorry, that's what I want to say. Suppose you don't have an, okay, so if you, if you are not mapping Freiman isomorphically onto the image, then I can exhibit some witness for that non-isomorphism, meaning a bunch of elements that do not have additive relations in the domain, but that do have additive relation in the image. So if we set this d, then it's some element of SA minus SA, and it's non-zero, because we assume that d is non-zero. And okay. So then, what can we say about phi of d? So phi of d, I claim, must be this expression over here, the difference of the corresponding sums in the image, because the two sides are congruent mod q. Right? Two sides are congruent mod q, and furthermore, they are in the interval from 0 to strictly less than q. Okay, so it's a slightly subtle argument, but the ideas are all very simple. Just have to keep track of the relationships between what's happening in the domain, what's happening in the image. But somehow I think the finite field case is quite illustrative of what goes wrong is similar to what goes wrong here, except here you have to keep track of a bit more things. Okay, so consequently, thus phi of d is congruent to 0 mod m, which is what we're looking for. Okay, so that proves the claim. Any questions? Yeah. Okay, so this part. All right. So we set d to be this expression. I claim this equality. Okay, so why is it true? First, the left-hand side and the right-hand side, they are congruent to each other mod Q. Okay, so why is that? Sorry? Yep.
Every part of phi should preserve, like the first two parts are group homomorphisms, and then we just take things mod Q.
Exactly. If you look at phi, where was it? Okay, so up there, you see that everything preserves, even though the very last step is not a group homomorphism, mod Q is preserved. Right? So even though the last step is not group homomorphism, it is so mod Q. So if you're looking at mod Q, everything is group homomorphism. So here we're good. Both are in this interval. The right-hand side is in the interval because of our assumption about everything living inside a short interval. And the left-hand side is by definition because the image of phi is in that interval. So especially if given that d is not equal to 0. Okay. Is that okay? Okay. Yeah. So it's not hard, but it's a bit confusing. So you need to think about it. All right. So we're almost done. So we're almost done proving the Freiman, the Ruzsa modeling lemma in Z mod n. So let me finish off the proof. So for each non-zero d in this iterated sum set, we would like to pick a lambda so that map up there does what we want to do. If it doesn't do what we want to do, then it is witnessed by some d, like this. Those are the bad lambda. Right? So that if there exists such a d, then this lambda is bad. So for each d that potentially witness some bad lambda, the number of bad lambda, okay, so i.e. such that phi of q, phi of d is congruent to 0 mod m. So here we're no longer even thinking about all the group homomorphisms anymore, or the Freiman homomorphisms. Just the question of if I give you a non-zero integer, how many lambdas are there so that phi of d is divisible by m? Remember that we picked q large enough so that initially, you are sitting very much inside this. Everything's really between 0 and q. So this dot lambda up there acts uniformly. So the number of such bad lambdas is exactly the number of elements in this interval that are divisible by m. Okay, so everything's more or less a bijection if you restrict to the right places. And the number of such elements is at most q minus 1 over m. So therefore, the total number of bad lambdas is at most, for each element d of SA minus SA, a non-zero element, we have at most q minus 1 over m bad lambdas. So the total number of bad lambdas is strictly less than q minus 1 So there exists some lambda such that psi, when restricted to A sub lambda, maps so Freiman S isomorphically onto the image. Yeah, somehow I think it's really the same kind of proof as the one in the finite field case, except you have this extra wrinkle about restricting to short diameter intervals, to short intervals. But the idea is very similar. Okay, so that's the Freiman model lemma in the integers. And let me summarize what we know so far, and so that to give you a sense of where we're going in the proof of Freiman's theorem. So what we know so far is that if you have a subset of integers, a finite subset, such that a plus a is size a times k at most, the doubling constant at most k, then there exists some prime n at most 2k to the 16th times the size of a, and some subset a prime of a such that a prime is Freiman 8 isomorphic to a subset of z mod nz. Okay. So it follows from two things we've seen so far, because by the Plöniker-Ruzsa inequality, 8a minus 8a is at most k to the 16th times a. And now we can choose a prime n between k to the 16 and 2 times k to the 16 and apply the modeling lemma. Okay, so that's where we are at. So you start with a set of integers with small doubling. Then we can conclude that by keeping a large fraction of a, right, keeping, no, I forgot to, okay, so very important. So there exists some a, which is a large fraction. Okay. So keeping a large fraction of a, I can model this large subset of A by some subset of a cyclic group, where the size of the cyclic group is only a constant times more than the size of A. So now we are going to work inside a cyclic group and working with a set inside a cyclic group that's a constant size, a constant fraction of the cyclic group. Question is why 8? Okay, so that will come up later. Okay, so basically you need to choose some numbers so that you want to preserve the structure of GAPs. Right, so that will come up later. And now we're inside a cyclic group, and you have a constant fraction of a cyclic group. Where have we seen this before? Right, so when we proved Roth's theorem, right, so that was the setting. Right, so you're in a cyclic group, you have a constant fraction of the cyclic group, and you can do Fourier analysis. Initially, you could not do Fourier analysis in just starting with Freiman's theorem because the set may be very, very spread out. But now you are a large fraction of a cyclic group, so we're going to do Fourier analysis next time to show that such a set must contain lots of structure, just from the fact that it is large. Okay, so that will be the next step. Okay, happy Thanksgiving.